Good afternoon, everyone, and welcome to our Fellows Public Talk series. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. It is my pleasure to introduce Radcliffe Fellow Laura A. Stevens. Each summer, portions of the Greenland ice sheet surface melts, forming brilliantly blue lakes atop the ice. Yet, these lakes, which scientists call superglacial lakes, can suddenly vanish, funneling billions of gallons of water to the ice sheet bed. Laura's work begins here, seeking to understand what causes superglacial lakes to drain in mere hours, and how emptying lakes impact neighboring lakes across the ice sheet. Ice sheets are often referred to as gatekeepers of sea level rise, with draining lakes acting as possible accelerants. One may think that if more lakes drain, more ice will fall into the ocean, causing sea level to rise. Laura's research complicates this simple narrative by testing whether the mechanism that causes vanishing lakes can also destabilize ice sheets on a broader scale. Through polar expeditions to populations of lakes in western Greenland, Laura and their team collected GPS data to assess if and how one lake's drainage may affect another. Their observations can be used to model how much Greenland melt will contribute to sea level rise and predict future global ice volumes against the backdrop of climate change. While at Radcliffe, Laura is focusing on a comprehensive lake drainage dataset gathered from 3 summers of fieldwork to explore the broader implications of melting ice on how ice sheets move and interact with the ocean. Their work will enhance our ability to forecast both the rates and consequences of ice melting, informing global response to climate change. The Q&A portion of the public talk today will be moderated by Professor Fiamma Straneo, Professor of Earth and Planetary Sciences, and the Gordon McKay Professor of Environmental Science and Engineering at Harvard University. And now please join me in welcoming Laura Stevens.
Thank you very much, Claudia, for that introduction. Thank you further to Jimena, Jin, Kayla, Jane, and Sharon for all that you do to platform our work as Radcliffe Fellows. I'm enormously grateful to be here in this year in your carefully constructed world. Scientific work is that of many hands, and it cannot be claimed that I am on this stage today without the efforts, findings, and support of many throughout the last 12 years or so, some of whom I'm delighted to say are present in the audience today. Sarah Doss and Fiamma Straneo, my PhD advisors. Thank you to Fiamma for being a willing moderator of the post-talk Q&A. Sarah's mom, Eva Borsati Doss, a steadfast supporter of this work and a Radcliffe alumna of entering class 1963. And welcome to glaciologist/oceanographer Lucy Wanzer. Can never have too many of those in the audience. To complete a scientific experiment on an ice sheet, you need dozens, if not hundreds, of people working together. Oops. I've tried to categorize those contributions and contributors here for everything that I'll show today, but I've likely missed someone in doing so, and I apologize to you. To the audience of fellows, thank you for your kindness this semester. What a pleasure it is to follow fellow Bob Kill, who reminded us yesterday, in kind, that we don't always need to be seeking answers. I will answer some of the questions I pose today, but in observing the natural world, it's only ever a partial solution, dependent on the time and place, dependent on what we can observe. Hopefully this talk will be enjoyable to those tuning in online. Thank you for being here. And finally, to the bots endlessly archiving this recording in data centers and cheapening my words into AI overviews. Cease, I beg you. It is not worth the carbon nor the water. I speak to you today from the vantage of a scientist whose contributions fit within the large international effort to observe, understand, and predict the rate at which the volume of water on Earth, currently locked up as ice, will cross that liquidus threshold and become water, raising the volume and surface height of our planet's oceans with its transition. The majority of my Radcliffe project is cataloging observations about a subject that I have returned to now multiple times in localities spanning both poles. This is the subject of ice sheet deformation and flow response to the drainage of lakes that form on top of ice sheet surfaces, lakes like the one shown here. Where and when do these events aid the ice sheet's accelerating contributions to sea level rise? When are they, sinfully, gratefully, business as usual for the ice sheet? The second half of my Radcliffe project that I've been telling myself I will begin immediately after I finish this talk focuses on a recurring topic that I have found necessary to address as a person who studies these systems, and that is the problem of observing a slow-moving, glacier-paced even, let's just get the pun out of the way early, a slow-moving system against a backdrop of increasingly apparent consequences. At what point does monitoring the problem give over to avoiding tackling the problem? I welcome questions, fellows and audience, on both halves. Let's begin with the shape of the problem. If we can define it, perhaps we can solve it. Today, Earth has two continental ice sheets, the Antarctic ice sheet over the South Pole and the Greenland ice sheet sitting just north of the North Atlantic Ocean. These ice sheets most recently got their start 33 million years ago in the Antarctic and just 3.3 million years ago in Kalalat Nunaat, Greenland. Together, they lock up roughly 65 meters of potential sea level rise. Cut an ice sheet in half like a loaf of bread, and you'll find mountain ranges underneath. You'll also find that, on the scale of continents, ice flows like a big pile of really cold, viscous honey. Glacial ice is no match for gravity and sags to assume a surface profile that best relaxes the stresses within the material, and the stress is imparted by the land surface that it rests upon. Glacial ice, the material, gets warped with time spent under strain, compression, shearing, fracturing, and this is truly the scientific term. Damage is the integral measure of these changes over a parcel of ice's lifetime, measured from the initial condensing into snow to its final act sloughing off into the sea, a conveyor belt ride that can last thousands to millions of years. Ice sheets are said to be in balance when, over the course of 1 year, the amount of snow that falls on them matches the amount of ice that melts into water and the amount of ice shed to the ocean as icebergs. The mass loss through iceberg calving is called dynamic mass loss because its rate has a lot to do with the flow dynamics of the ice sheet. How fast is the ice sheet moving along its bed, conveying ice into the sea? What processes might quicken this conveyor belt ride? This question has been the subject of much research in recent decades. It's arguably the rallying call for glaciologists worldwide. That's because the ice sheets that we know and love today are not in balance. For the Greenland ice sheet, balance switched to imbalance in the mid-1990s, when the ice sheet started losing mass more than snowfall could replace each year. From that mid-1990s time point until 2018, the Greenland ice sheet added 11 millimeters of sea level equivalent to the world's oceans. When we track these ice sheet mass contributions to sea level rise with other sea level rise components, the ocean expanding as it gets warmer, and water currently stored on land moving into the sea, we track the slow accelerating ramp of global sea level rise of the past decades. These observations are meticulously provided by thousands of scientists that form the Intergovernmental Panel on Climate Change, IPCC, a global organization that collates climate change findings from across fields to provide the scientific consensus on the physical, chemical, and biological changes to our planet. A useful aspect of the economic half of the IPCC's work is detailing multiple possible future global greenhouse gas emission scenarios. That's these acronyms SSP 8.5 and 2.6 that you see on this graph. Scientific groups then use these emission pathways to project what Earth's temperature will be like in the future, and in turn, how much sea level will rise. Which emission scenario we follow does not matter much by 2050. Either way, when Taylor Swift and I turn 60 years old, the seas will have risen by roughly 20 centimeters over the course of our lifetime. My entire lifetime is in this graph, as is true for anyone else in the audience born after 1971. By 2100, which emissions pathway we follow has a huge effect on sea level, with a difference of 30 centimeters between the two scenarios shown. Melt from glaciers and ice sheets will contribute roughly half to this sea level rise. Finally, by way of introduction, sea level rise contributions from ice sheets enter the global ocean, but the impact of these additions is felt very locally. The reality of the changes are increasingly coming into focus and increasingly becoming just the world we live in. The work of co-corresponding authors Lara Cushing and fellow Rachel Morello-Frosch was highlighted on WBUR 2 weeks ago. Their work starkly reminds us that sea level rise hazards are not equitable. In mapping the number of hazardous facilities at risk of flood events due to sea level rise by 2100, these authors found 5,500 such facilities along US coastlines if we follow that high emission scenario shown last slide. Further, if coastal communities today have an above average linguistically isolated households, neighborhood residents identifying as Hispanic, households with incomes below twice the federal poverty line, households without a vehicle, or non-voters, or they're renting, the likelihood that one of these hazardous facilities is within 1 kilometer from the community increases by up to 41%. The high emission scenario is the pathway that we're on, and the ice sheets will not stop their mass contributions to the sea. This is because the climate of today is not cold enough to regrow ice sheets. For melt driven by warming ocean water, this means that as ice sheets retreat back, often into deeper water, ice flows faster, and then the retreat takes place even faster. For melting driven by warming ice temperatures, this means that as the ice sheet surface lowers in altitude due to melting, it meets warmer air, and at these lower altitudes, just melts even more quickly. These are the realities of positive feedback loops that we live on the planet we live on, and the social purpose driving the research I present today is a decadal effort to try to understand how lakes like this one fit into this ice sheet conveyor belt. This is a supraglacial lake at 68 degrees north latitude on the Greenland ice sheet. It's a few kilometers across, and encircling the water, you might be able to see a bathtub line of the lake's maximum extent that summer, likely reached a few days prior to when this photo was taken from a helicopter. The lake has lost some water through the region circled here, where the lake has breached its shallow brim and water is spilling out into a surface stream that cascades into a crevasse, splintering the ice sheet. This feature is a moulin, French for mill, and this water will thermally bore its way down through 1 kilometer, over half a mile, of the ice to the ice sheet base. Once there, water rate will pressurize the interface, affecting how quickly the ice sheet slides as water travels along the ice sheet base and eventually reaches the ocean. This is a relatively small waterfall, just about 20 meters across. This is one way water exits lakes and impacts sliding, but there are other ways. Roughly 10% of lakes that form initially rest happily within their basins, where the ice is generally compressed together and unlikely to fracture. Until an event, some trigger promotes fractures to open within the basin. There's plenty of water available to drive these fractures to the bed in a process termed hydrofracture, and that lake can then drain entirely within a couple of hours. As this flood reaches the ice sheet base, the kilometer of ice above is uplifted on the order of half a meter, and the blister of water at the base of the ice causes the ice to slide quickly until the flood travels away from the lake. We've been piecing together what events could trigger hydrofracture events for the 5 lakes that we have in situ observations for. For these handful of lakes, we observe the ice sheet to start moving faster and to uplift off of its base in the half day leading into the hydrofracture event. This precursory ice deformation leads to tension at the ice sheet's surface, and the ice can only withstand so much stress until it fractures. Usually, the source of this precursory perturbation can be located as a nearby moulin, where water's first delivery to the bed uplifts the ice a little bit. This suggests that hydrofracture initiation may be a quite localized process. But the problem is that there are actually thousands of lakes that form annually on the ice sheet, and with observations only around a handful of single lakes, we know very, very little about how these systems work and interact. I'll next take you through another different example with some very new data we recovered from summer 2024. But first, the volumetric reference that you've all been waiting for and never wanted. The closest pond to where we sit today is Fresh Pond Reservoir, Cambridge, Mass. 02138, with a volume of 1.5 billion gallons and a lake margin of 3.6 kilometers. Fresh Pond is located distance of 2.6 kilometers from the NAFL Center. I will use its metrics to give a sense of scale moving forward. Back to the ice sheet, here's another set of lakes. One in the foreground with two lobes, and a big one in the middle background. Fresh Pond for scale at the front, and don't think too much about the issues with the perspective of the helicopter snapped image for the moment. At this orange line here, there's a useful linear texture in the ice forming on the surface of the lake. That linear feature is here on the zoom in. In the middle of this photo, there's a sensor mast fashioned from PVC pipe drilled into the ice sheet. And anchored around the base of this PVC pipe is a sensor tracking the pressure of whatever is above it, be that air, snow, water, every 5 seconds. We convert this pressure measurement into a height of water above the sensor, and then we use an elevation model of the empty lake basin to calculate the volume of this lake. We also recovered a sensor from Lake 2A, located about 7 kilometers to the north of Lake 2B, and in this way we can track the fill and drain cycles of lakes. As we move through this time series of 18 days in mid-July 2023, we see both lakes to steadily grow in volume. The volume is listed in number of fresh ponds on the left vertical axis. Some satellite images are cloudy, but the in situ sensors provide a continuous record. Lake 2B, shown by the black line, begins to overspill on July 17th, and then both lakes completely drain on July 21st, with Lake 2A draining at 4 times the volume of Fresh Pond, and Lake 2B draining at about the volume of 1 fresh pond. Zooming in just on July 21st and changing the vertical axis to the drainage rate, that's the rate of water draining down through the hydrofractures, we observe that Lake 2A in blue begins its drainage around 1800, followed in sequence by Lake 2B, which kicks off around 2030. Both lakes are gone within the span of 4 hours. And for about an hour in there, the discharge leaving Lake 2A surpassed the mean discharge of Earth's 3 largest terrestrial waterfalls. At Lake 2A's peak drainage, the rate of water loss is equivalent to a bank-full fresh pond disappearing in 20 minutes, which is about the amount of time it takes me to jog around this pond. By luck, we have some incredible photos of these lakes in the day immediately following their drainage in 2024. At this orange location here, on the day after the drainage, you can see flat-bedded rivers flowing into a moulin embedded along a linear feature. That linear feature is the hydrofracture, now squeezed back shut. Viewing these features from above, you can observe the spiky, scalloped nature of the drained lake bed, as well as pick out some annual ice layers of the ice sheet in the region of the river that's spilling into the moulin. This is incredible footage, and I'm exceedingly grateful to the engineer Marianne O'Call, who took this video on her phone, and for the chance to share this imagery with you today. Okay, let's zoom out to the big picture now. The Greenland ice sheet is large, and thousands of lakes form on its surface each summer. In 2015, Amber Leeson published a study tracking the maximum elevation of lakes at present and where these lakes will climb inland to by 2050. The region I've been showing you is at around the location of letter D in Amber's figure. Gwen Flowers, another notable glaciologist, penned in 2018 the problem very well. She wrote, though lakes are projected to form further inland on the ice sheet with rising temperatures, whether lake drainage will be effective at these inland lake sites is unclear. The situation is unclear because in 2018, we did not have the observations in hand to figure out how one lake drainage may affect a neighboring lake, if at all. To move forward here, we needed to pluralize, to understand how individual lakes drain, to figure out possible triggering interactions between close neighbors, and then to move up to the scale of interactions between populations of lakes across the full altitudinal range where they form on the ice sheet. The shape of the problem is no longer how one lake works, but how thousands may interact. Okay, part 2, pluralize. In 2016, the European Space Agency launched a constellation of satellites by the name of Sentinel. Thanks to ESA, you're guaranteed an image from these sentinels at minimum of every third day in this region of the Greenland ice sheet in the southwest. Each pixel in this image is a 10 meter by 10 meter square patch of the Earth's surface. This image is taken at the beginning of May in 2022, before summer has begun, and the ice sheet is still shrouded in its winter coat. This red box will become important, but don't worry about it too much yet. As we move through the 22 summer season, our eyes can track lakes forming beneath the clouds. These lakes fill and drain from one image to the next with some complex spatial patterns and timings that we can't quite keep track of with our own brain. We can, however, use pixel tracking algorithms to keep track of all the blue pixels that touch other blue pixels so that by the end of the season, we've mapped the maximum size of all 342 lakes that formed in the summer of 2022. Okay, now find the red box and find lake number 78. Trace the margin with your eye. Lake 78 is in the bottom left of the red box. Commit this lake shape to your memory. When we look at every image of Lake 78 taken by Sentinel in 2022, the time of these panes goes from top to bottom and then from left to right. We can track Lake 78's initial pooling in June to its complete disappearance from view from one image to the next in mid-July, to the bathtub ring of the lake's margin that stubbornly remains as the melt season wears on, to the rich textures of the ice surface being blanketed by first snowfall and winter's onset in September. Before ESA launched Sentinel, in a good year, we'd be lucky to have a fifth of the number of these satellite images of this lake. And the images, by comparison, would be lower resolution, very blurry. But this is the modern age, so we'll use the high-res images to our advantage. What immediately stands out to my trained eye is that for our lake number 78, has kilometer-scale bright linear scars crisscrossing its basin on the day after water has left the scene. These are the hydrofracture scarps that I showed you in helicopter images, but now we can see them from space. You can even track a stream at the bottom right that feeds this lake basin and now spills into the hydrofracture scarp. We cataloged 11% of those 342 lakes in 2022 to have these scars, indicating drainage via hydrofracture. A further 14% of lakes drain by a moulin that forms at the margin of the lake. Once this moulin forms, the lake drops in volume and a stream appears that is spatially inside the margin of the lake at its high stand. We actually find the majority of lakes to be water rest stops on the meltwater highway. These lakes form along superglacial stream pathways where water is temporarily impounded before making its way down the ice sheet. Most often, the next destination is yet another lake. And finally, 5% of lakes form each summer, but then just freeze over as the winter begins. These lakes don't transport their water out of the scene. Taking this back to the map, the lakes are plotted by their drainage mechanism. What about the spatial arrangement of the gold hydrofracture events could inform us as to how these events are triggered? Well, we know that as the melt season turns on in June, Lakes fill and drain at progressively higher altitudes, moving from left to right over this region. So there is a background rate of lake drainage that just simply tracks the elevation that the lake forms. We are curious, however, about hydrofracture events that occur in clusters of groups of too many lakes draining in too short of a period of time to still fall statistically within our expected number of daily lake drainages. I've connected those groups of hydrofracture events in black lines. The groups are still small in size, never comprising more than 7% of the total number of lakes available to drain. If we could lift this ice sheet completely off the ground, we'd find those mountains with high ridges alternating with low valleys. The valleys here are shown in blue colors, and you'll notice that some of these hydrofracture clusters fall along the same troughs. Maybe the flood of one lake is triggering a neighbor down valley. Now, we can't magically disappear the ice today, but what we can do is keep track of where that water reaches the base of the ice and keep count of where that water would most want to travel and at what pace. Like in terrestrial rivers, water wants to flow downhill along the valley floors, but unlike in terrestrial rivers, this subglacial water is being squeezed by the kilometer or so of ice sitting above it. The pathway out of this pressurized situation is along valleys and towards regions of thinner ice, which is towards the west, viewers left, of the ice sheet region. I'll play this film again. Each frame is a new day in 2022 from June 1st through Halloween. And you'll see the lakes forming and draining as shapes that climb up the ice sheet surface. Focus your eye on the sinuous nature of the blue features. These are the subglacial rivers that form every summer. The darker the blue, the larger amount of water is flowing through the river. As summer progresses, in a matter of weeks, the water flow narrows from broad swamps into focused rivers. These rivers use their thermal energy to vertically incise the base of the ice sheet, tunneling up space for water to flow faster. Remember, this is the water that's flowing at the base of the ice sheet. It's not the surface rivers that I've shown you in photographs. Okay, even I know that this is way too much information. We've thoroughly pluralized at this point. But to recap, we've surveyed an ice sheet region from space that's the width from Cambridge to about the Connecticut River, from left to right, and pretty much the full height of the Commonwealth of Massachusetts. We've looked to see which lakes drain by hydrofracture. We didn't find that many, but we linked those in gold that happened too quickly for us not to be curious about them. Our next task is to specify, to figure out any and all causal interactions between these hydrofracture events. We are curious as to their triggers. If we can identify what sets off a hydrofracture event, we may be able to better predict how the behavior of these events will change in future. Let's take it back to our handful of statistically curious clusters. With a lot of planning and a little bit of luck, we instrumented hydrofracture events of 2 of these sets of clusters with Global Navigation Satellite System, GNSS monitoring stations, more commonly known as the US-only GPS. These stations are the 22 black triangles with 4-letter names. We logged the position of the ice every 5 seconds at these locations for 2 summers. We've seen this group of lakes in the red box before. We decided to begin our regional GNSS array instrumenting these lakes because over the last 24 years of time, in satellite images, we observed the central and southern lakes, L1A, L1B, draining close in time 4 times as often as the lake to the north, labeled L1C. In many years, like in this photo series, the lake to the north simply freezes over at the end of the summer. What is the underlying physical explanation for this behavior? This is a question we can ask with the GNSS data. We can use the GNSS data to track the position of the ice sheet's surface in 3 dimensions, east, north, and up, and then invert these surface positions to calculate what the stress of the ice sheet's surface is as the lake drainages take place. In this video, red regions of the map will show ice under tension, where it is stressed and wants to fracture. Blue regions of the map show ice under compression, where ice is squished. The time series at the bottom shows stress evolution at the 3 lake basins, and we see that as the L1B lake drainage first occurs, the high stress region from this lake drainage event encircled by the growing black loop, extends to cover Lake L1A to the north, which then drains via hydrofracture. All of this activity takes place within 12 hours. What is happening to Lake L1C in the north at this time? We observe that this lake actually becomes a little more compressed as the drainage events to the south take place. This is really good evidence supporting the fact that stress interactions between lakes are spatially complex. Neighboring basins can be placed in either tensional or compressional stress, which would then either promote or inhibit further drainage. Here we can also connect the observations from satellite images that the lake to the north commonly freezes over at the end of the season, and see how they align with the slight compression of this region of the ice from our GPS observations and modeling. Expanding back to that hydrofracture cluster of 5 events, there are 3 more hydrofracture events connected in black here. When we peer at what is happening with the hydrology beneath the ice sheet, we see that all 5 of these events, circled in red here, lie along the same subglacial valley, along the same flood pathway. This conclusion still needs to be further tested with additional modeling, but an initial hypothesis to pose here to describe what's happening is that the lakes can interact moving down flood pathways, where the flood event ensuant from one hydrofracture travels beneath other lakes, uplifting the ice as it does to provide the tension needed to trigger another hydrofracture event. Now, the lakes located down flood path are not too much of a problem in terms of impacting ice sheet dynamics. The lakes at lower elevations are already forming and draining. However, what happens if we turn our attentions to the lakes located higher on the ice sheet up to the right? Can flood events lower down trigger lakes at higher elevations to drain? Our final task is to regionalize these observations. The experimental setup goes something like this. Instrument 3 groups of lakes at different elevations and measure whether and how the ice warps between them. Ask the question, do the drainages of lower lakes advance upper basins towards fracture? Here are our 3 groups of lakes moving up the ice sheet from left to right. And the final plots I'll show you today are these type of time series that show us how strain rates across the lake basins change as the melt season progresses. For these plots, on the vertical axis, positive values of strain rates calculated between station pairs show you when these station pairs are moving away from each other, when the ice is getting stretched across the lake basin. This is when fractures may be opening. The negative values of strain rate show you when the ice is getting squished, when fractures are unlikely to be opening. At this time here, for the lowest elevation set of lakes, we see the magnitude of strain rate fluctuations during 2 hydrofracture events of those lakes L1A and L1B that I've already shown you. This accordion-style stretching of the ice happens during the fracture events, and then the ice gets squished back together as the flood leaves the region. We also observe in these time series that there are some strain rate fluctuations prior to hydrofracture. These are very useful observations because they show us that lake basins can withstand some low level of stretching without leading to fracturing and lake drainage. Okay, so with all this stretching happening at the lower elevation lakes, the next thing we can do is move up the ice sheet to the middle set of lakes, where we see that at the time when the lower set are hydrofracturing and setting off floods across the ice sheet, strain rates in the middle set of lakes are really unbothered. Very little stretching or squishing activity is going on in these time periods. The next thing we can do is move further into this melt season. And for this middle set of lakes, we observe that similar accordion-style strain rate fluctuations leading into the big hydrofracture event on day 215. Finally, we can move to the highest elevation lakes, where we observe very minimal strain rate excursions during the lake drainages of the lowest elevation lakes and the drainage of the middle elevation lakes. This small bump in strain rates that you see around day of year 210 is the expression of a moulin lake drainage of one of the lakes in this higher elevation set, but otherwise things are very quiet at this upper elevation. Now, the takeaway from these records is that the GNSS observations allow us to reject the hypothesis that accelerating ice flow at lower elevations triggers hydrofracture of lakes at higher elevations. Inland basins are really quiet when lower elevation floods take place. And for the first time, we can see how isolated these hydrofracture events are from each other when we look up and inland on the ice sheet. This is great news because it means that there is not a runaway relationship between hydrofracture events when moving up the ice sheet. More likely, as lakes form higher on the ice sheet, hydrofracture events will happen, but the events will not happen faster than the melt that's already moving up to higher elevations and forming these lakes in the first place. From this, and in closing, I want to leave you with some preliminary conclusions from first passes through this data set that we'll be continuing to work through for some years yet. We've collected a data set that allows us to move from single event observation to regional and perhaps ice sheet-wide understandings of triggers to hydrofracture. First, we observe that hydrofracture event triggering demonstrably occurs between close neighboring lakes and likely down subglacial pathways. Second, we're kind of surprised to find that this interlake triggering does not extend inland over really far distances. Inland basins are relatively quiet as lower elevation lakes drain. And third, this means that the new hydrofracture events taking place at higher elevations will likely advance inland across the ice sheet at roughly the same rate as surface melt. This means that these hydrofracture events are not an additional accelerant that we haven't yet factored in to ice sheet to projections of the ice sheet conveyor belt bringing ice to the sea. And yet, this conveyor belt is not slowing down on my lifetime or in future generations' lifetimes. So, how to end? Where to go from here? I often return to Rachel Carson at this impasse. Ray, as her friends called her, is writing here in 1962 on the environmental harm of indiscriminate DDT pesticide use. She wrote, "To have risked so much in our efforts to mold nature to our satisfaction, and yet to have failed in achieving our goal, would be the final irony. Yet this, it seems, is our situation." From this acknowledgement of irony and from Ray's life spent observing the natural world, an answer that works for me in terms of what to do in this situation, working on climate change issues amongst a backdrop of sea level rise. An answer that works for me is to keep observing, to not jump ship, but maybe to put out the fire. So thank you for listening, and I look forward to your questions.
Thank you, Laura, for that wonderful presentation. My name is Fiamma Strano, and yes, I work at Harvard, but I had the pleasure to meet Laura many years ago when she was a PhD student, and I was at the Woods Hole Oceanographic Institution, and Laura did some of her graduate work with me. And then just for reference, I'm an oceanographer, so I'm at the receiving end of everything that melts.
Sorry about that.
Yeah. I also had the pleasure to do some field work with Laura. And I think prior to her coming to Cambridge, the last time we met was a random encounter at a small airport in Greenland, where, flight delays. So then we even had dinner, which was very nice.
That's when I decided to apply to this, actually.
Excellent. See? Great. So maybe we'll start with, all of the audience start submitting questions, both the audience here and online, with a more sort of bigger question, more profound, and building on the Rachel Carson quote, which is climate change is a multi-generational problem. The science that you do is also multi-generational science. We need to understand ice sheets better. They are melting, they are moving. We need to understand the details to make projections. How do you see yourself in this path where you know very well you won't have all the answers next year or even in 10 years or more?
Thank you for that question. Also, thank you for doing this today, Fiamma. So the multi-generational aspect of this science is, I definitely see it in all of the work that I do, because in many ways, with the advent of new technology, new satellites, we can now observe the ice sheets in much higher resolution than we could even do in the 90s. So in the mid-1990s, GPS technology becomes energy efficient enough to be able to put these instruments onto ice sheets, and then we get the first observations of how ice sheets move kind of every hour. By the mid-2000s, we get how the ice sheets move kind of every second. Also in this time, since beginning my PhD in 2012, we have new satellites entering Earth's orbit and taking better and better resolution images, both in space and time. So even from proposing to do this field campaign, new satellites were launched, and the amount that we could see from space radically increased during pretty much the timescale of my PhD to now. So I think that's one multi-generational aspect, is that the technology that allows us to observe our Earth is changing with generations. Another aspect, and this is really cool because there are papers written in the 80s, the 1990s, before we had these observing capabilities, that put forth these hypotheses that are kind of just really profound, and now we have the observations to go out and test them. So I feel very lucky to be able to test kind of some of these initial theories put forward. And hopefully maybe I'm putting some theories forward that other people will disprove or reaffirm in coming decades.
Great.
Okay.
Thank you. Let's see, some of the online questions. There's a question. It's how do you get information on the basal topography under the ice? And there's also a parallel question. One of the audience members interested in, as the ice slides, there's maybe the lakes are, as the ice moves, the lakes are moving, or the depressions associated with lakes are moving with the ice, and how does that interplay with the basal topography?
Those are great questions. So we know the basal topography beneath the ice also from kind of engineering feats that happened in, I want to say, the 1990s and early 2000s, where we got good enough at putting radars under the arms of airplanes to fly these radars across the ice sheets in Greenland and the Antarctic in these very regular patterns. And what this radar is doing on the airplane wing is sending energy down into the ice. It goes through the ice, hits off the base, bounces back up, and is collected by the radar. And the time that it takes for that radar pulse to move through the ice and down to the bed and back up to the airplane is how you know the thickness of the ice and then can map out the bed beneath it. So a huge advance in our field was certainly continentally mapping out the base of the ice sheet and actually getting for the first time the thickness of the ice sheet. And I remember those papers coming around by Matthew Morligam and others in kind of 2013. So this is very recent knowledge that immediately is super impactful for incorporating just our knowledge of how much volume of ice is on Earth, how that volume is changing and turning into sea level rise. Second question on depressions of ice moving beneath lakes. This is a really fun aspect of these superglacial lakes. So the bed topography beneath lakes is fixed. It's not changing that much in time. But the questioner is right. The ice is kind of always slowly flowing about 100 meters per year over this topography. And what happens is, as the ice flows over this basal low, you get a basal surface dip at the top that stays in place. It's pretty much locked to the bed basal low. But any surface features that form, holes from moulins or fractures, they still advect through this space at about 100 meters per year. So you get these kind of scars of past surface hydrology remaining, these remnant scars kind of remaining in these basins for on the order of 20 to 30 years. And certainly figuring out how that slow advection of surface features plays into the triggering hypothesis is maybe something we can start asking about. Maybe now, maybe there's enough time that has passed with high resolution images to track this. But yeah, so the bed stays fixed and that ice flows through this region and that lake basin stays fixed in place. This is very helpful for instrumenting these lakes because they do not move from year to year. That's different on Antarctic ice shelves.
Great. Very interesting. So, building on instrumenting lakes, you didn't show too much of your field work, but I sort of picture you as somebody who flies around in a helicopter and then uses all her running training to run around the ice sheet and put little sticks here and there. Can you tell us a little bit about how you collect the observations?
Sure. That's a perfect description, except I'm usually not running because I don't know if you noticed in some of these images, but there are these kind of potholes of water that form on the surface of the ice sheet. So I'm kind of very carefully stepping around that. And in more recent years, taking trained mountaineers to help us with the safety aspects. Yeah, but the fieldwork is a huge part of this, and I could have given a full hour's lecture on kind of the logistical challenges of even creating these observations. It's a type of work that I feel like is learned through mentorship, just in terms of how you piece together a lot of constraints on where you can go on an ice sheet, what the weather conditions are, how many people you can fit into a helicopter. It's about 3 in a pilot. How much weight you can carry in that helicopter. It's about 500 kilos. That's maybe 4 GPS stations. You can move these weights around in bags beneath the helicopter or within the helicopter body. So all of those questions come to play. And I think, Fiamma, we were talking this morning, you mentioned that you teach a class on fieldwork here, and that something you include is making a checklist.
So I asked Laura, what's on your checklist that maybe wasn't there at some point?
Yeah. So in one of the 3 seasons that we were most recently working in Greenland, we were out installing these GNSS stations, and that process requires using a hand drill attached to a kind of thin but long auger, and you auger down into the ice sheet about 2 meters, and then you fasten together metal poles that you put in this hole, and then you put your station sensor or kind of batteries on top of these poles. You need the poles to stay in place because then it can track the movement of the ice. And something that is definitely on my checklist now that wasn't initially is that you don't just need 1 hand drill, you need 3. Because there was a day where we were finally able to get to that highest elevation lake sites, and the mountaineer working with us that summer was drilling wonderfully perfect holes, but that drill bit just sheared in the wrong place, and then we were headed back into town. Luckily, there's really good hardware stores in all of the towns in Greenland, which I'm sure you've frequented many of these.
Right. Great. So I feel like you've described the lakes, and there's a parallel again with Rachel Carson. You're a bit like a naturalist trying to understand this very complicated system. You use observations in the field. You use satellites, and I know you use numerical models. Can you tell us a little bit how, in your mind, do you put all these things together?
It's very nice to be called a naturalist, because I feel like that is, yeah, at the core of this work. And I feel like putting all of these different observation, modeling, satellite images, putting all this information together is just a constant switching in my mind of physical scales. And I tried to do that a little bit today with showing you all Fresh Pond. When you're flying in a helicopter above these features, it's tough to understand the scale. When you're standing on the ice sheet next to these features, it's such a strange environment that it's also tough to remember in the moment when you're thinking about your field checklist. Oh, what actually is the spatial kind of distance that I'm interacting with in this environment? So I think that it's really, maybe as all naturalists, it's trying to get information and intuition about these systems from any angle that's possible, and then trying just re-going through my field notes, re-going through the photos as I'm looking at the data. And eventually, over, I don't know, a PhD's worth of time, you do develop some intuition for this on what 1 kilometer cubed means in terms of ice. And that from that intuition, you can really start to do the modeling work with an eye to what is actually a realistic modeling result and what is not. And I think that's a very nice way where being in the field, seeing these features directly feeds into the modeling, directly feeds into what I can confidently assess from those satellite images. Yeah, so I think it's just, yeah, it's just constant thinking about these things when running around Fresh Pond, too.
That's great. Thank you. So going back maybe to the bigger implications of some of your work, how do you think about you're contributing to the understanding of ice sheets? How does this connect with what society might want to know about sea level rise? And there's a parallel question of Antarctica, which you've mentioned, but you showed mostly Greenland results. And we know that's the larger, eventually will become the larger player in sea level rise.
Absolutely. So I think this is something that I've actually struggled with in a recent year, because I feel like in starting this project to observe lake drainages across a really big region, the concluding evidence that we found, or the kind of top line conclusion of the paper that's in review right now, is the fact that these lakes are quite isolated from each other moving up the ice sheet. So this is actually overturning a hypothesis that's out there in the field at the moment, that you would see kind of a domino style or chain reaction type drainage of these lakes moving inland, and that would allow these hydrofracture events to destabilize the ice sheet, move it faster into the ocean. So in some ways, I view the big implications of this work as being a research group, a research team that actually goes out and tests these hypotheses, that these lake drainages aren't included in the big ice sheet models that give us sea level rise projections. That's partly because until now we don't understand how they work on the scale required to include them in the models. So I would say that's one, contextually, that's where I see this work fitting in. And then you mentioned Antarctica. So Antarctica is kind of just tipping into contributing sea level rise every year. And a big difference between Greenland and Antarctica is in Antarctica, the ice is so massive that it flows out across the onto the sea, and you get these floating ice shelves. And these floating ice shelves, some of them also have lakes like this. And in 2002, the glaciology community was quite surprised to see that one of these ice shelves about 80 kilometers across, which this distance, I tell my students in Oxford that that's the distance on the train from London to Oxford, but that's not a good distance now. But anyways, it was 80 kilometers across, and it collapsed in a couple of weeks, and we think that it was due to these hydrofracture events like I've shown here, splintering that ice shelf. I have worked on a project with collaborators trying to instrument the lakes that form on these Antarctic ice shelf ponds, and it was actually very difficult because that water moves laterally across the ice shelf. So this is a way, I feel like working in this region of Western Greenland is a way to get observations of these processes and have more confidence that the data we're getting back can give us new information that we can use. Maybe we can use that to understand the Antarctic ice shelves better when they may collapse is a kind of leading question for glaciologists thinking about Antarctica. Or maybe there's something we can do from our satellite intuition now looking at the Antarctic that can be the link there. Yeah, so I think with working in the polar regions, there are limitations as to where you can go, and I feel like working in Western Greenland allows us to understand what's happening with Greenland hydrofracture events, and maybe we can carefully take some of those observations and apply them to the Antarctic future, the future state of the Antarctic ice sheet. Yeah.
Great, thank you. We only have a couple minutes left, so last question I'm sure everybody's curious about is, what's next for you? And I'm gonna add I'm curious if some of the interactions you've had with the Radcliffe community or any of the experiences of moving to Cambridge, being here, have shaped some of what's next.
This is what I said I'd start tomorrow working on. But what's next? I feel like what's next is, given that the satellite observations are so good now, we can really see what's going on from space. So I feel like what's next is really perhaps expanding what we've seen in this region of Greenland to a Greenland-wide area. And then another avenue could be using satellite observations in different sorts of ways than we've used them before. So there are now satellite constellations that can take pictures at different times as they're moving across a scene. And you can difference those images to give you a 3D profile of what the surface looks like. And you can now task or ask these satellites to, hey, shoot images of this same location, every day, give me something. And I feel like there's a big open space for, now that we have the in situ observations, moving into more of a satellite-based observation of deformation. And then to bring it back to Radcliffe, I feel like, it's kind of hard to process all the interactions between the Radcliffe Fellows as they happen. It kind of feels like first year of undergraduate, because, lakes are forming and draining, relationships are forming and happening all the time. But I feel like one thing that I'm really taking away from this is that you need to really like what you do. And for us, Fiamma, we do these projects that are long in duration, maybe 5 years from proposing idea to submitting a paper on it. So I think one main thing I'm taking away is, okay, I need to be really excited about the next question, and it has to have a social purpose behind it. So if anyone has a question they want answered with satellite data, you can send it my way or put it in the chat. Great.
Wonderful. So thank you, Laura, for this great presentation and sharing your perspectives. I'd also like to thank all the audience here and the online audience, including all the people who submitted questions, and I know I didn't get to all of them. You can find out more about future programming and watch videos of past events at radcliffe.harvard.edu. And that's it. Thanks everybody for joining us, and maybe one more round of applause for Laura. Thank you.